So this leads me to categorical variables. Right, so these are all categorical variables. Your gender, your race, the school you're going to. These are all categorical variables. The way we put them into regression lines is that we assign a dummy variable. A dummy variable takes the value of either 1 or 0. It's a binary variable. If you have just two categories, so in the case of gender we have female and male, you only need one dummy variable. For the case of race, right now we use the census, it's like 7 categories. We're going to use a very, very simple version of it. We're going to do 3 categories of white, black, and other. You only use 2 dummy variables. Here in the case of 2 schools, assuming that everyone goes to just these 2 schools, how many dummy variables should I have? 1 dummy variable. So the rule is the number of categories minus 1. Number of categories minus 1. There's a reason behind that. We just got done talking about multicollinearity. Multicollinearity is when 2 variables are highly correlated with one another. So let's think about an equation that has both a dummy variable for female and a dummy variable for male. So that means if you are female, you get a value of 1 in the female variable and a value of 0 in the male variable, right? So if you know that female is 1, does that make the variable in male random, or do you know that value as well? You know it. So this is an extreme form of correlation, right? It's perfect correlation. So if you have perfect correlation, you definitely have multicollinearity, but you have of the worst kind. So if you thought your standard errors were big under just multicollinearity, when you have perfect correlation, your standard errors explode to infinity, meaning you can't estimate the standard error. So we have to drop at least 1. And what happens is that when we drop that 1 ends up in the constant. So the constant represents a base group. Right? Constant sits and represents a base group. So if I write an equation that says wages is equal to a constant plus beta 1 female, meaning that it takes on the value of 1 when it's female and 0 when it's male, plus beta 2 white, plus beta 3 black, plus beta 4 Yuga. The person that is in the constant is going to be a male who has a race of other, because both of these would have to be 0, and is at UK. So the constant would represent that base person. Now let's think about different combinations to see how this changes. Right now I haven't really added a slope, right? So this is another way of doing multiple group testing. So you learned how to do 2 sample means, right? So think of this as many people you can combine here. And now you just have a simple t-statistic to make the comparisons instead of doing all the nasty stuff we made you do in chapter 10 and 11. Now, here's the other part that's hard about interpretation. When it was a continuous variable, the slope was pretty easy to understand, right? You just add everything up by 1 unit. Here, these betas don't really tell us the female effect. They tell us the female effect relative to the base. Right? That's what they tell us. How much better is... So let's go back to the base. Who's in the base?
Other males. Or males.
Other males at
UK.
Other males at UK. So beta 1 here tells us the effect of other females at UK versus other males at UK. Right? So categorical variables, while they're really neat in getting a hold of these categories that don't have a number associated with them, their interpretation can be tricky. Their interpretation can be a little tricky. Now here's something else that I want you to be careful with when you're using categorical variables. These are catch-alls. This is all the stuff that we don't know, but it's associated with someone that's in that group. And the reason that's dangerous is that people will often point to discrimination, or even worse, causal inferences associated with race or gender based off these things. And the problem is that it's catching everything about that group. that's in there. As we add more explanatory variables, we might be able to tease that out. So one of the things that people do in discrimination studies is they'll start with a very basic model that has just race, and they'll say, okay, these are the means. And then they'll start adding socio-demographic information along the way to see, is it just race or is it something else? So let's add in poverty. Let's add in education. Let's add in presence of both parents at home. Let's add in other things like that. What should happen is that if it is not racial discrimination, the parameter on race should get smaller and smaller and smaller as we add in all these other things. If it is discrimination, and after we add in all those things and race is still significant, then we can start saying, okay, something's weird going on here. Because that dummy variable of race only captures stuff that we can't see associated with that group. So anything we can't see associated with that group will be stuck there in that dummy variable. And that includes a lot of things that are beyond race. It just happens to be that race is the common denominator. So if we run that regression and we don't include poverty, that'd be really bad. If we run that regression and we don't include education, that'd be really bad. Because we already know that those average levels are different between the groups. And what we want to do is we want to control for those differences. To say, no, it has to be something other than poverty. It has to be something other than education. Same thing with gender. Right? We don't want to run a regression with gender and not include those variables. Because if we do that, then we'll say, oh, look, we have these differences in wages that are totally associated with gender. Well, of course, we ignore levels of education, we ignore levels of experience, we ignore all those other things, which could also be different between the groups. And that's something I want you to be careful about, because people don't do their due diligence when they do these things. They'll often report to you means between those groups, and they'll say, look, we have a problem. But they haven't controlled for any of the other variables that are associated with those two groups. All right, so we have these dummy variables to take on the values of 0 and 1. They're called dummy variables, indicator variables. It's only two groups, binary variables. But what they're doing is that they are defining a group by turning on ones and zeros. So just like we did here, we were able to describe a person without actually using any continuous variables. We were able to describe a person without using any continuous variables here by just using a group of variables that are 1 or 0. So going back to the programmer's salary as an extension of the problem involving the computer programming salary survey, suppose that the management also believes that the annual salary is related to whether the individual has a graduate degree in computer science or information systems. So we have the years of experience, the score on the programming aptitude test, and whether the individual has a relevant graduate degree, and the annual salary for each of the sampled 20 programmers are shown on the next slide. So now we have, do they have a degree or not? If it's yes, we'll turn the variable on, so we'll give it a value of 1. If it's no, we turn the variable off, and we give it a value of 0. So if you're putting this data into Excel, you'd have 1s and 0s in that column. 1 if they have a degree, 0 if they don't. So here is our regression equation, and now has an x3. We get the ANOVA output. We have our sum of square regression, our total sum of squares. The F went down a little bit. Here we're explaining 8468. Before it was 8342, so we've been able to add roughly 3% more information by adding in this dummy variable. The adjusted R squared is 8181. The previous R squared, adjusted R squared, is 8115, so that's that penalty effect I'm telling you about. That squashes that 3% change to less than 300. And if we include that degree, notice that the p-value says that it's not significant. And I think that's going to continue in this particular area, that it's going to become more of a trade rather than a professional graduate degree, because they can test you now. Right? If they really wanted to, your interview would start with you going to a computer and they would say, write us a program in Fortran that can solve this problem. And so, as we get more complex variables, we have to add more dummy variables. Just think of the levels that that particular category can hold. You subtract off 1. That 1 is still there. It's just in the base. So your base becomes more and more complicated as you add more and more dummy variables into your regression line. Care must be taken in defining and interpreting those dummy variables like we just did when we wanted to say what was the relative differences between two individuals. Alright, so here, for example, If we want to find people with different levels of education, we'll have in the base a person with a bachelor's degree, and then we'll have two other groups, one with master's and one with PhD. So the very last part that I'm going to show you has to deal with dummy variables, is that you can use dummy variables by themselves, but you can also use them as an interaction. So